I hope I'm audible. I will start after 6, so let's wait for some time so that people can join. Okay, it's 6 p.m. so let's start. People can join in the middle also. Hello everyone, welcome to the live session for the course Introduction to Semiconductor Devices, and this is week 5. Okay. So let me introduce myself first if you are joining the class for the first time. I am Ananya. I am a PhD student in the Department of Electrical Engineering, IIT Kanpur. My specialization is microelectronics and VLSI. I mostly work in fabrication of devices. I will be the TA for this session. So I conduct this live sessions on every Tuesday from 6 to 8. So as always, we will start the session with a brief overview of the topics for this week. So let's start that. Okay, and before that, if my voice is not audible properly, if there is any disturbance, then please let me know. I might need to turn off the fan because there might be some background noise. If it is okay, then it's fine. I will continue. So what we have learned in this week, in week 5, we have discussed about little bit about quantum mechanics in first few weeks. Then we discussed about semiconductors, like different types of semiconductors, doping, and how we can determine the resistivity and mobility and all those terms associated with semiconductors. Mainly we are discussing about silicon. Now after that we started discussing about semiconductor devices. So when we talk about semiconductor devices, first device we know that is the PN diode, and before discussing about PN diode, basically the diode behavior, the rectifying behavior, that we will discuss in this week. In last week we discussed about PN junction, and as I mentioned earlier that it is very important, like PN junction is a very important topic in semiconductor devices, because in many devices, like in other types of devices also, we will see PN junctions. Okay, for example in MOSFET, in BJT, we will see PN junctions. In BJT, voice is audible? Okay, great. For example, like we will discuss about BJT, bipolar junction transistors, there is also PN junction. So there will be two PN junctions in BJTs. Okay, So PN junction is very important, and in semiconductor we say that junction is the device. Okay, interesting phenomena happens around the junction. So that is why in last week we discussed about PN junction, and today we will discuss about PN diode. Basically, the way the diode behaves. Mainly, we will discuss about voltage versus current relation. Okay. So first topic that we have discussed, what is the band diagram? We have discussed earlier that energy band diagram can give us many information when we are discussing semiconductor devices or semiconductor in general. Okay, so first thing we studied in this week is energy band diagram of a PN junction under different conditions, forward bias and reverse bias. Okay. So this is our PN diode, this is the P side, this is the N side, and different biasing condition, how we draw it. So this is the notation, and I am applying a voltage VA. If VA is positive, that means the positive terminal is connected to the P side and negative terminal is connected to the N side, then it is forward bias. And if VA is negative, that means negative terminal is connected to P side and positive is connected to N side, then it is called reverse bias. Okay. Now for normal energy band diagram, VA is equal to 0. That means there is no applied voltage, no external field is applied, no external forces applied. That means there is no current because our diode will be in equilibrium. Okay, and when there is no current, what it also implies that our EF is constant. So how we draw the energy band diagram for VA equal to 0, that means in equilibrium condition. So first always draw the metallurgical junction. What is metallurgical junction? This, and we often denote it with x equal to 0 if we are considering this is our x-axis. Okay, so this is my x equal to 0, and energy band diagram is energy levels versus position. Okay, so we first draw the metallurgical junction, then we will draw the constant Fermi level. Okay. So our Fermi level is constant because there is no current, it is in equilibrium. Always remember, equilibrium means Fermi level is constant. Then away from the junction, we will draw the energy band diagrams for P side and N side as it is. Okay, because we know that everything is happening near the junction, and away from the junction, these are known as quasi-neutral region. These are mostly neutral regions, so neutral P and N side. So we will draw the energy band diagram in these areas. Okay, so this is P side, this is N side. So it will be, valence band will be closer here, and here EC will be closer in N side. Okay, let's say this is our EC, and somewhere here it will be EI, intrinsic Fermi level. This will be EV, EI. Now we will join these two smoothly. Okay, we already know that our electric field is linear in this region because of the space charge region. Linear electric field implies parabolic potential, and we have learned that potential and energy levels are related, like voltage and electron volt. Okay, that's all. So we will join it smoothly. It is parabolic, we already know that. There will be no discontinuity here because this is against silicon, this is against silicon. So this is the same material, and from electrostatics we know that there will be no discontinuity. this is under no bias condition. Now what happens in forward bias? Forward bias means VA is greater than 0. Okay, what happens in forward bias? When VA is positive, then there will be another electric field which will be opposite to the built-in electric field. Okay, so built-in electric field was in this direction, so our applied electric field will be in this direction. So because of this applied electric field, some of the carriers from p side, that means the holes, will move towards n side and some electrons will move towards p side. Okay, overall we will get a current. Overall our system will not be in equilibrium because we are applying an external force as a voltage. Okay, so what will happen? Majority carriers diffuses into the depletion region. Okay. Holes will enter into the n side. First it will enter into the depletion region of n side. It will come to the edge of the depletion region. We consider that for all our derivations, we consider that there is no recombination or generation in the depletion region. It will come to the edge of the depletion region and there will the holes will diffuse. Okay, and eventually it will recombine. Okay, in the quasi-neutral region. So what will happen? Net space charge region will decrease and our W depletion will also decrease. Okay. So how the energy band diagram looks in that case? So when VA is greater than 0, there will be some flow of current because electrons and holes are moving. So now our EF is not constant. Now what I mentioned earlier, that EF is the average, it's like the average energy of electrons in a system. Okay, if there is more number of electrons, EF will be higher. Okay, there are more electrons. If there are less electrons, the average energy of the electrons, or overall the energy of the electrons, will be also lower. Okay, so when we are applying so when we are applying a positive bias in the P side, whether it is P side or N side, that does not matter. In case of semiconductor, when we will apply a positive bias, then EF will decrease. It is like taking out of taking some electrons, you are taking some electrons out from the system. And when you apply a negative bias, that is like adding some electrons. Okay, so in number of electrons will actually increase. That means our EF will also increase. Always remember this to draw energy band diagrams under applied bias. Okay, so I will write it down also. When we apply positive voltage to a semiconductor, it does not matter whether it is P-type, N-type, just like positive and negative, you remember this. This will be useful when we will study about MOSFET, MOS capacitor. Okay. EF decreases, electrons decreases basically. Similarly, when you apply negative voltage to a semiconductor, EF increases. Now what will happen when we apply a positive bias to the P side? So let's see. Again, I will first draw the metallurgical junction, that is my x equal to 0. I'll first draw everything away from the junction. Okay, so let's consider that we are drawing energy bands like similar to potential, right? And potential we define with respect to something. Okay, there is no concept of absolute, so we are considering that our n side is our reference. So say EF was like this, and then do you have any question, or if you are unmute by chance, then please mute yourself. Okay. Our EF will decrease here. So this is the P side. See, if you don't unmute, then I have to unmute everyone. If you have some doubt and if you want to say something, then please write in the chat box or ask me to unmute you. Otherwise, there is lot of disturbance. Okay, so I am drawing EF slightly below because we are applying positive bias to the P side. Okay. Now, as I mentioned, that away from the junction, the bands will look as it is, like the P side will look as it is and N side will look as it is, and our overall EG will be constant, right? So this is my EV, say this is EC, EF, this is EC. The diagrams may not look like up to scale, but you get the idea, right? So this is EI. Now again we will join this smoothly. Okay, so yeah, the diagram is not very correct, but you get the picture, I hope. Now our barrier, potential barrier, actually got decreased, and how much it got decreased? So this was Q VBI, and this is Q VBI minus VA. So how we draw this kind of energy band diagram? We first draw the metallurgical junction, then EF. If there is no current, EF is constant. If we are applying bias, then we will draw the EF with respect to bias, considering these 2 points. Okay, and then we will draw the EC and EV away from the junction, and then we will join the EC and EV, keeping the band gap as same. Okay, here you can see the band gap is not like in the picture, it's not same, but actually it is same. Okay, so that's how the band diagrams look in forward bias. And what happens in, okay, now this barrier got decreased, some of the electrons will move towards this side, electrons will move, holes will move in this side. Okay, so overall we get a current from P side to N side. So this is our direction of current. Okay, what happens in reverse bias? Opposite kind of thing happen. We apply VA as negative, that means we are applying negative potential to P, So overall, I don't have much space. So if this is my is f in n side, then this will be bit higher in p side. So this is EV, this is EC, say this is EV, this is EC. I'm not drawing the EI levels here. Okay, it will be like this. So this barrier height actually increases due to the reverse bias potential. And how much increase? VBI, because VA is negative now, so overall it is plus. Okay, and because we are considering reverse bias, so we write it as VR, say reverse bias voltage. Okay, so what another thing we learned in the course, that in forward bias diffusion of carriers is important, and in reverse bias drift of carrier is important, because now we are like there will be some drift, we will learn about it later. There will be drift of carriers, but those are not majority carriers, those are minority carriers. Okay, so here drift current is important. You can think about it like this: we are applying negative bias voltage here. Okay, there are some minority carriers holes in n side in the depletion region, because we are considering the depletion region is there is no moving charge, but that is not entirely true. There is no moving like majority carriers. All the electrons in the n depletion region of n side has moved towards the p side. Okay, that's how we are getting the depletion region. But there are still some minority carriers. There are still some minority carriers holes, and those minority carrier holes actually moves in the reverse bias condition. Okay, we are applying negative bias here. The minority carriers holes will try to move in this direction. Okay, and in the p side minority carriers will be electrons. Those will try to move towards the positive potential side, because in this case reverse bias VA will be negative. Okay, so that is why drift current is important. So they are under this drift, under the electric field. Okay, they are moving due to not due to the concentration gradient, they are moving due to electric field, and we know that that kind of current we call as drift current. Okay, that is why drift current is important in reverse bias and diffusion current is important in forward bias. But you should remember that overall individual electron and hole currents are same and constant, and that's how actually we do the derivation of current in PN junction, PN diode. Okay. Now let's try the, I will not do the derivation. Even in the course also the derivation was not exactly given, so we will talk about how minority carrier injection and how minority carrier moves in PN junction due to forward bias. Okay, not minority, like majority carriers from one side it moves, and they are the minority carriers in the other side. Okay, you want to say something? If you have any doubt, there was so much background noise from your side, so that is why I muted everyone. But if you have any doubt, I can unmute. Yeah, now you will be able to unmute yourself. this is our diode. Okay, so what happens, applied positive VA, that means forward bias, it injects minority carriers. Okay, holes will move towards the N side, they are the minority carriers in N side, and vice versa. Okay. So because of this injection, there will be a creation of non-equilibrium. The equilibrium condition, that is the diffusion, is stopped due to the drift, due to the inbuilt electric field. So that equilibrium condition will not be there now, and this leads to a non-equilibrium carrier injection. We have talked about non-equilibrium carrier injection earlier, and we will use those same concepts here. Okay. So this injection creates Now here we make again a very important assumption that there will be no recombination and there will be no generation in the depletion region. Okay. So this is the edge of the depletion region in N side, this is the edge of the depletion region in P side, this is 0, and this is our equilibrium. So this is P side, this is N side. We are drawing the minority carriers, and what are the minority carriers in P side and N side are the holes. We are denoting it as Pn naught. P is the hole concentration, N is N side, naught is denoted. This is the equilibrium. This is what was present in equilibrium. Okay, what is this value? This is Ni square by Nb. Similarly here, minority carriers are electrons, and these are in P side, and in equilibrium the value was Ni square by Na. Now some holes are moved towards this side, say this is the concentration of holes, and we are considering long diode. For short diode it will be different, but we are considering a long diode, and from our earlier discussion of non-equilibrium carrier injection, we know that the carriers will decay exponentially, and ultimately it will go to the equilibrium condition. Okay, we are considering that whatever number of holes were injected from this side to N side, all of those holes reach the edge of the depletion region. Okay, this is an important assumption here. These are assumptions, not exactly correct, but for our purpose it's good enough. Okay. Similarly, this is our number of injected carriers towards P side, and it decreases exponentially, and finally it matches with the equilibrium concentration. Okay. Please go through the earlier lecture videos where it was discussed, non-equilibrium conditions were discussed. Okay. So how the exponential decay happens, we know that it happens like exponential of minus x by Lp. So Lp is the scales for the diagram. This will depend on this Lp, right? So these are usually in microns. Okay. If you remember the calculations we did, so these are in micron level. Okay, and we are considering our injected carriers and overall our number of minority carriers at the edge of the depletion region. We are denoting it like this, Pn at Xn. Remember, I have not written P and naught because this is not equilibrium concentration. Similarly, this we can denote as N in the P side at the edge of the depletion region, and similarly this has an exponential decay as x by ln. Okay, ultimately there is a decay, that is why we are writing it as minus x in this side because x is positive here, and in this side there to denote that there is a decay we are keeping x as plus because our x is already negative in this direction. Okay, so these is the minority carrier, these are the minority carrier. Okay. Now we know this expressions Ni exponential electron concentration can be written as Ni exponential EFn minus EI by kT, and P is okay. Now what is the product of N and P? Remember, this N and P product is not equal to Ni square because this is what I mentioned earlier, that Np equal to Ni square, which is known as the mass action law, that is valid for equilibrium condition, and that is valid when when the semiconductors are non-degenerate, right? This we have studied earlier. So what is the product of N and P? There will be this extra term, that is exponential EFn minus EFP by kT. Now what is the difference between Fermi level of N side and Fermi level of P side? From the energy band diagram we can say that this is our applied voltage, okay, QVA. So product of N and P is Ni square exponential QVA by kT. That means our number of excess carriers, excess minority carriers will depend on the applied voltage. Higher the voltage, there will be more number of excess minority carriers. So we know that how our NP at minus XP will look now. This is NP naught exponential QVA by kT. There will be these many numbers of excess carriers. Similarly, at the edge of the depletion region, of course, it will decay exponentially with distance because of recombination. Okay? And Pn at Xn is Pn naught exponential QVA. This expressions are very important. You should remember this. If you want to know how we can calculate all the currents like very clearly, the derivation was not discussed in detail in the course because the professor is trying to give you the bigger picture, like how the movement happened. Derivation you can find in any book, right? The important thing is that we should remember our what the excess carrier depends on our applied voltage, and that's how our excess carrier the current in PN junction depends on the applied voltage basically. All the derivation steps are given in the book, so I have shown you the book earlier, right? So this is me, and if you are interested you can study. So these are our excess minority carriers at the edge of the depletion region, okay? And while we are doing this derivation, this expression, what is the important assumptions we are taking? See, assumptions are important. while doing, you already know the diode, maybe you already know the diode current equation, right? We have learned it earlier also in BTech first year, all those courses. I equal to is exponential qv by eta vt minus 1, those kind of expression. But again, you should know that while deriving the equation, we are taking some assumptions, and assumptions are important, and in many cases we are ignoring a few things. So you should know where the assumptions does not work. Okay, so here we are considering that no generation recombination, in the depletion region, and we are also considering low level injection, right? Now I'll very briefly draw the energy band diagram again. This is in forward bias, and we will see how our, so this is p side, n side, how our Fermi levels vary. So this is n side, EFN, and this is p side, that will decrease because we are applying positive bias, EFP. Okay, and this will be EC, EB, now this is the this is the Fermi level for electrons. We have learned about quasi Fermi levels, right? Quasi Fermi level is different actually. So what will happen, say this is xn, this is minus x. Okay. So this is the Fermi level of n side. How we know that in equilibrium, like far away from the junction, there will be equilibrium. The semiconductor will be as it is, and we know that when there is equilibrium, the Fermi levels for electrons and holes will be at the same position. But if there is a non-equilibrium condition, that is what happening near the junction, near the depletion region, in that case the change in minority carrier Fermi level will be higher, but the change in majority carrier Fermi level will be almost same. Okay, I will check your question. I'm just drawing the Fermi levels. Okay, so we are considering that there is no recombination, so electron Fermi level will be same like this. Now overall, away from the junction in the neutral region, the electron Fermi level will come to the Fermi level of majority. So electrons are minority carriers. Here the number of electrons is more, that is why the electron Fermi level in this region is close to EC, but overall it will come back to the equilibrium position, that will be same as the majority carrier Fermi level, that is EFEN. Similarly, for holes, EFP is same here, and in this region there will be excess holes, so the Fermi level of holes will be closer to EV in the side, but overall away from the junction it will come closer to the majority carrier Fermi level. please brush up, like if you already, I hope you remember all these things, but please brush up your quasi Fermi level concept for this diagram. Okay, so this is how the Fermi levels, actually the quasi Fermi levels vary in p-n junction in case of forward bias. Concentration of carriers. Okay. That diagram was given to you, I don't remember. Like the system is a minority carrier. So these are minority carriers. I think the diagram was discussed in the class, right? I think in the last class also we discussed like how the carriers change. P and it decrease a bit like this. Please check the notes from the last class. I think I showed this graph, N and P graph. Something like this. I remember I have discussed that even though we are saying that there is the depletion region, there is no charge, but there are some charge like this, right? Because say this is the whole concentration, it's higher in P side, it decreases, and this is the Ni square by Nd. This is the whole concentration here, and here it started N as Nd, and it decreases like this, and this is Ni square by Na, something like this. Please check the notes from the last class. I think I have discussed it. Okay. This is how the carriers vary. Okay, so this is what happens in forward bias. What happens in reverse bias? Okay, this is again in forward bias. What happens in reverse bias? How the minority carriers vary. So this is again X. These are my edge of the depletion region. This is my equilibrium condition, that is my Pn naught, and this is P side, this is N side, and this is Np side, Np naught. And how my minority carriers vary? Minority carrier concentration is actually 0 in this position, because the minority carriers are actually moving, like because of drift, it is moving towards the other side. Okay. So that is why the concentration is 0 here. Okay, you remember, I hope you remember the diagram from the lecture videos. Okay, because of the drift, because the minority carriers from P sides are moving towards the N side because of the applied bias, because of the electric field. Okay, that is why the concentration goes to 0 in this region. Okay, so drift current dominates in reverse bias condition. Now we will discuss about the current component. We already know that now whether it is in forward bias or whether it is in reverse bias, our device is not at equilibrium because we are applying some bias voltage. Okay, we are applying some external force, and our electric Fermi level is not constant. Okay, how the Fermi level varies, we know that if we apply positive bias, our Fermi level goes below because number of electron is like decreasing. And if we are applying a negative potential, that means we are supplying some electrons, so overall the Fermi level goes up. Okay, that's how our Fermi level varies. Our Fermi level is not constant, we are not in equilibrium. So when we are not in equilibrium, that means there is some current. Okay, so we know that in n side our carriers look like this, minority carriers. We know that in forward bias, so let me write it in forward bias. In forward bias, we are getting current due to diffusion of minority carriers. Okay, holes are diffused towards n side, holes are minority carriers, and because of this diffusion we are getting some current. Okay, so let me write the carrier concentration. So this will be Pn at xn, and this value is exponentially decaying. It's minus, now I am writing the exact expression by Lp. Okay, this I mentioned that it decreases exponentially and with the order Lp. This is the exact equation. Similarly in P side, Npx is equal to Np minus Xp exponential x plus Xp by Ln. Now what is this maximum value? What is this maximum value? We have already discussed this, right? So this is our Pn xn is Pn naught exponential QVA by kT. Similarly, Np minus Xp is equal to Np naught exponential QVA by kT. Now remember, these are our minority carriers, not excess minority carriers. What will decay? What carriers will decay? Excess minority carriers will decay. Okay, so to calculate the current, you should find the excess minority carriers. Okay, that will be like delta P. If you calculate, that will be Pnx minus Pn naught. Okay, similarly you can find excess minority carriers in n side. Now what will happen? Our total current density will be Jn diffusion plus Jp diffusion, right? This we already know, we have studied about currents in semiconductors. So this is QDN. We know how we can find the diffusion current. QDN, that is the diffusion coefficient, d delta n by dx, right? Whatever the excess carriers, they are going to diffuse. Okay, so d delta n by dx. And for holes, we know that this is the negative sign, because the concentration gradient is, if the concentration gradient is in this direction, holes will diffuse in this direction. Okay, holes diffuse, or any carriers diffuse from higher concentration to lower concentration, and because of that actually this negative sign comes. And in case of electrons, because again the current direction is opposite, we consider that's how the current conduction flows. The direction of current is opposite to the direction of electron flow. That's why we consider this as positive. Okay, don't get confused. So this is Vp d delta p by dx. Now this is for forward bias. So if we do all the calculation, there will be this x term. Okay, if we do this derivation, and finally what we will get, q dp p n naught by lp dp n p naught. Okay. Or we can write it as q dp ni square lp into nd plus qd. So this is the na and this term we call as JS, reverse saturation current, because when if our device is in reverse bias, then V will be negative, so this term will be very less, and so this is approximately our current will be equal to minus of JS. Okay, so this is our reverse saturation current. So this part is our current due to the holes, right? So if we want our hole current component to be higher, for example, if you look at this figure, you can see that hole current component is higher compared to the electron current component. What it indicates is that hole current is higher, that means the doping density in n side is lower. Okay, this has this inverse relation. If you want to increase the hole current component, you have to decrease the doping density in n side. Okay, and similarly it's same for electron current component also. You have to decrease the doping density of the other side. Okay, so this is one important observation from the current equation. So this current equation we already know. We know it like I equal to Is exponential QVA by KT minus 1. Okay, this we have been using, like maybe you are using from BTech first semester, second semester onwards, but this is how we get the actual current equation from this kind of a derivation. Okay, here again these are again assumptions. We are considering that individual electron and hole current components are continuous. You can see here, so this is the hole current component, this is continuous. This is the electron current component and this is continuous. This is the hole current component, this is continuous, and overall our total current is constant everywhere. Okay, that is why we are only considering our current at this position and at this position. We are considering that there is no recombination of carriers in the depletion region, so whatever our whole current is in this position, that is same as this position. Okay, so we can sum this up and get this total current. Again, our whatever our electron current component at this position, it is same as this position, and we can sum with the whole current component to get the total current. Actually, we know the whole current component at this position at xn and electron current component at xp. Okay, but we can consider that these are continuous, and that's how we are considering calculating our total current component. We are saying that this total current is constant. That is why this equation is valid everywhere in the junction, everywhere in the diode. But we are actually calculating only at the edge of the depletion region. If you want to calculate, say, diode current, derive the expression of diode current at this position, say in the neutral region, then you have to find the majority carrier whole component, because you can see this is maximum here, this is almost zero, electron diffusion current is almost zero, but we don't know this. For us, most convenient position is at these positions, because we know what is the excess minority carrier due to the injection, and that's how we are calculating, and this is valid everywhere. Okay, I hope that you understand this concept. This is the basic fundamental concept of PN junction. We are considering everything near the depletion region, but we can calculate the total current density everywhere else, but current is continuous. This is the first thing we are considering, and that's how we are saying that our current, total current near the junction is same as everywhere. Next, there were few small topics. So first one was capacitance in PN junction. Okay. There are two types of capacitances in PN junction. If you are more interested, please go through the textbook, because it was briefly discussed, so I am also just giving you an overview. So first one is our depletion capacitance or junction capacitance. Okay. Depletion capacitance or junction capacitance we mostly consider in reverse bias, because it is dominant in reverse bias. Okay. So this is easy to understand. Depletion capacitance is easy to understand. So this is P and N. There are these fixed charges in P side, there are these fixed charges in N side. Now this is like the separation of charges. Okay, we know what is capacitance, we know what is parallel plate capacitors. There will be positive charge, there will be negative charge. It is separated by dielectric, right? So this is something like that. This we can visually understand that it is something like a capacitor. And when we apply a reverse bias voltage, this is VA, which is negative, then the width of the depletion region changes, because it is like the applied voltage is taking out the carriers. Okay, that's how the depletion width actually increases. So W depletion, when VA is equal to 0, that will be less than W depletion when there is an applied reverse bias voltage, right? So the depletion width is changing, that means our overall charge is changing, and because of that, because C equal to dQ by dV, so we are getting a capacitance. And the capacitance value, the depletion capacitance, if you do all the derivation, it was discussed in the class, the value will be epsilon silicon if we are considering a silicon diode, and this will be W depletion. Okay, and we know that W depletion expression is 2 epsilon silicon by Q, Na plus Nb, Na into Nb, Vbi minus Va. If it is reverse bias, then it will be Va will be negative, so it is plus whole square root. Okay, so this is the depletion capacitance. What is important here? C depletion is inversely proportional to Vbi minus Va, because W depletion is in the denominator, right? You should remember this, how the depletion capacitance is related to applied bias voltage. Everything else is constant. Another type of capacitance is diffusion capacitance. It was not discussed in the class in detail, so I am also skipping. Diffusion capacitance is significant in forward bias. In reverse bias, we are saying that depletion capacitance is important. We are applied negative voltage to the P side. That means we are applying a reverse bias. That is actually changing our width of the depletion region, and that's how we are changing the capacitance. What happens in case of diffusion capacitance, very briefly, there is this excess carriers, and we know that this excess carrier actually depends on the applied bias voltage. Okay, so with the applied bias voltage also, this excess carriers will change, right? And actually that is how we get the diffusion capacitance. It is not easy to visualize as depletion capacitance. In depletion capacitance, we know that there is this separation of charges. It is not as obvious as diffusion capacitance is not as obvious, but if you are interested, you can read the book. The only thing I'm saying is that diffusion capacitance is dominant or important if we are applying it in forward bias. Okay. Now you must have remembered this graph, log J versus Va. This is in forward bias, this is in reverse bias. This graph tells a lot of things about an actual diode, not an ideal diode. What we know, in case of ideal diode, this will be a straight line, this will be like almost a straight line after few kT. But in case of real devices, there are some non-ideality. Till now, the derivations we have done, we are considering some assumptions, we are ignoring few things. But if you consider everything, if we try to calculate the current, considering every phenomena that is going on, every physical phenomena, then our actual current will look, actual current versus voltage graph will look bit different. So we call these are non-idealities in PN junction. So in non-idealities, first we learned about junction breakdown. How much time I have? Okay, I'll not go into the details. You must have watched the lecture videos. I'm just giving you an overview. I want to go towards the questions. What happens in case of junction breakdown? This happens in reverse bias. Okay. Breakdown means in reverse bias, ideally we don't want any current conduction. We get a very small current that is equal to Js, but if there is a large current that's flowing, then we call it as a breakdown. Now there are two types of breakdown that can happen. First one is Zener breakdown. this is happen this happens because of electron tunneling. Let's say we are applying a very large reverse bias voltage, and it is so large that our band bending is very high. So this is my QVBI plus VR. That this EV is actually higher than EV in, so this is P side, this is N side, right? So we know that there are electrons below the Fermi level, below the valence band. So these states are filled. Now if this EC, this side conduction band is below below the valence band edge from the P side, and if this barrier is very small, then electron can tunnel towards this side. We learned about this tunneling in quantum mechanics when we studied. We said that if there is a finite potential well, then electrons will mainly stay in this region, but there is a probability that electrons will leak out outside of this well also. This is something similar to that. Or if there is like a barrier in between and electron is moving from this side to this side, even though electron energy is less than this barrier height, there is still a probability that electron will reach this side. So if this goes very high and this barrier becomes very small, then electrons can move from V side to N side, and that can lead to a breakdown that is known as Zener breakdown. So what it does, it results a large current in reverse bias. Now another type of breakdown is avalanche breakdown. So what happens in case of this kind of breakdown? High energy electrons under electric field in depletion region. You know there is this inbuilt electric field, and when we are applying a bias, that actually adds another electric field, and in reverse bias the overall electric field is actually higher. Okay, so electrons get higher energy, like it gets very high energy due to this electric field. And if the electrons get very high enough energy, then what happens? Those electrons actually hit the lattice, the atoms. They can that energy will be transferred to an atom, that will release an electron and also create an electron hole pair. Okay, so this creates EHP, electron hole pair, and overall there will be this multiplication. So now one electron and hole pair is generated, that electron will again hit another lattice atom, it will create another electron and hole pair, and overall there will be a lot of electrons and holes. Those are under electric field and those will move, and overall there will be a large current, and that is known as avalanche breakdown. Okay, these are undesirable. So that leads to a large current here in this region. This voltage we known as the breakdown voltage, and if you can check the data sheet of a diode, you will find this. We don't want to operate our diodes near the breakdown or even above the breakdown region, above the breakdown voltage. Okay, if we want ideal behavior of a diode, ideal rectifying behavior of a diode. So this is the first region, and in the second region what happens, the current is actually bit more uh, compared to what we expected as JS. This is because when the reverse bias voltage is high but it is still below the breakdown voltage, there will be the width of the depletion region will actually increase. And what we have told earlier, that in the reverse bias, the current is due to the drift, and drift of what? Drift of majority carriers. I mean, drift of minority carriers. In the p side, electrons are actually moving. In the n side, holes are actually moving. As the width of the depletion region increases, there will be more number of minority carriers, and those will move, and overall the current will be slightly higher. Okay. This is the reason 2, and reason 3 is when, so all our assumptions is we are considering no recombination and generation in the depletion region while deriving the current in the forward bias, but there will be some recombination and generation, especially at the lower voltages. So it reflects this. The reason 3 actually reflects this. This region is our ideal region, ideal diode region, and in region 4 what happens, this is the high level injection region. We are considering that whatever the minority carriers that are being injected, that is much lower than the majority carriers, but that assumption is not correct in for high level injection, and so our current actually deviates. Current is much it does not increase with that intensity. Okay. And this 5 is the we are injecting so much electrons and holes towards the other side, that overall we are getting an ohmic behavior rather than a rectifying behavior. So this rectifying behavior is for the diode, and in this region, so I think it was discussed that the series resistance part of this quasi-neutral region becomes very important and becomes dominant, so it behaves like a resistor, like a normal resistor. Okay? So these are the non-idealities of p-n junctions that we often ignore. Okay? Next I will go to the questions. If you have any doubt, you can ask. I am taking a break. I'm shouting at the top of my voice. Let's do the first question. This is not essentially a p-n junction question. This is like a basic semiconductor question. So there are few options. I think the options are not required, but since it is given in the question, I'm just writing it down. So a silicon bar is doped with donor impurities Nd as 2.25 into 10 to the power 15 atoms per centimeter cube, and intrinsic carrier concentration is given as 1.5 into 10 to the power 10. Assuming complete impurity ionization, what is the equilibrium electron and hole concentration? Yes. In the course, if you remember, we learned this curve with respect to temperature. Initially, this ionization happens. This is our extrinsic region, and this is our intrinsic region. If we are considering, say, this is N, right? This is our complete ionization region, and this value is Nd. This time at which this complete ionization happens, it is important. If you are interested, you can check for different semiconductors when it happens for certain doping concentrations. Those graphs will be given in the textbook, and you can find it at Google also. If there is no complete ionization, then remember, we cannot say that our N is equal to Nd. If our temperature range is, say, here, okay, then we have to consider that how many donor atoms are getting ionized and do the exact calculation. But since it is given as complete ionization, in most of our calculation we are considering this, because around room temperature at 300 Kelvin, for most doping concentration of silicon we get complete ionization, so we are considering that. In that case, our life is simple, calculations are easy. We can say that our N0 is equal to Nd, which is 2.25 into 10 to the power 50, and P0 is Ni square by Nd. This is our 10 to the power 5 per centimeter. Next two questions are based on this diagram. Here you can see this is the metallurgical junction, x equal to 0, this is xn, and this is minus xp. These are our equilibrium. This line is for equilibrium minority carriers. These are the excess carrier and they decay exponentially. This is our depletion region. Okay, this is P side, this is N side. So the question is, if a PN junction is forward bias, then for the minority carrier distribution, answer the following questions based on the graph. So question 2 and 3, I'll give 2 questions based on this graph. So the first question is, I think we don't need options, but it's given in the question, so let me give you. P side is more heavily doped, the N side is more heavily doped, both sides are equally doped, both sides are lightly doped. So what is the correct option? Which side of the junction is more heavily doped? Answer A. Okay. Yeah, correct answer is A, because why P side is more heavily doped? We know that Na into Xp is equal to Nd into Xn. So our Xp is less than Xn. That means our Na is greater than Nd. Okay? Here. This value is smaller. That's how we are getting. For the next question also we have the same graph. The question is, excess is N and P NP. Yeah, axis is N and P, but x-axis is the I mean the this axis is the x-axis, right? Vertical axis is the y-axis is the concentration. Okay, so yeah, we can consider xn and xp. Yeah. This axis is x. Which region exhibits a larger I think you can. I have unmuted everyone. Yeah, you can unmute.
Actually, in this question, uh, there is the shift towards left hand side, right? The slope of this, the according to this graph, the equation governing should be ln np naught by ni square minus qva by kt, right?
Sorry, can you repeat? I didn't understand what you were saying.
Uh, this is n naught p naught, right? The y-axis is n naught p naught and the x-axis
Y-axis is
is
not and not P naught.
uh,
So these are minority carriers. Not not. You
uh,
see, there is this not symbol is not given.
no
Not
no no,
symbol.
I'm saying it is generally product of np, right?
I mean, see, for this side actually, for this negative side, they are plotting this NP, okay, minority
uh,
carriers. So this is the plot for minority carriers actually,
uh,
okay. And in this side where x is positive, they are plotting this Pn. Don't get confused with this notation.
okay.
Is that what
But
you are
the
thinking?
slope should be governing the equation n naught p naught is equal to ni square exponential qva by kt, right?
Hmm. QVA
Yeah.
by KT, yeah. But
uh,
here this P and N is different. This is not this N.
Yeah, how do I relate it with the actually length of the depletion region or whatever axis is given over here? You understand my question? The
No.
slope for this particular graph
Hmm.
is n naught p naught by x, right? I mean pn by x, delta x.
The slope you are saying this slope.
Yeah, yeah, yeah.
No, this slope. So this varies exponentially. So how it varies? It's like x by LP. That is the second question actually. I mean, this is not x by xp. So this is minus x plus xn. The equation that I gave you earlier. See, this P naught exponential QVA by KT, this is a constant term. This is a constant value, this point.
Uh,
This we are multiplying with this expression exponential minus xn by LP. This is x dependent and that's how this is varying. The vary, how
okay.
it is varying, it is not dependent on the applied bias. Only the injection of minority carriers depends on the applied bias. How it varies, how it decays exponentially, that's how the normally minority carrier diffuses. Normally you remember the non-equilibrium carrier kinetics we have studied in earlier weeks. So this is again same. Okay, so this is constant. Of course, different for different VBA. This peak value will be different, but how it decays, it depends on this diffusion length. It depends on the diffusion coefficient and all these things.
I am not clarified in the one steady state carrier equations. Can you clarify on that? Steady
Steady
state. That
state.
is, there was a question in assignments stating that a laser is illuminating N type or P type semiconductor on one side, and the generation of carriers was given. It was week 4 or week 3, I guess. Can you clarify that question, because
So
that will be helpful in this, I
okay, okay.
guess.
So I have not checked the questions, but you are saying that this is in week 3, and if you can quickly find the question, I will discuss in the next week because I have not checked the questions. I
Okay.
hope that you will be there in the next class and we can discuss, because I don't want to say something that is not correct.
Ah,
So I will
ah,
go through the questions, I will solve it by myself and then explain in the next class. Is
okay.
it fine?
Yeah, okay.
In week 3, right? I have noted it down, and some laser
I'll tell
question.
you the exact one. It is
And and also remember that I will explain after the deadline of the assignment is over, because I was instructed to do that. Okay, I cannot explain the
okay.
assignment question before the deadline.
No, this is we are in week 5, right?
Okay, okay. So if the deadline is over, then I can explain.
Okay. Uh, it is in week 3, question number 4.
Question 4. Okay.
Okay. Yeah, thank you.
So here,
This question.
yeah, this question I will note it, write it down. I think you are clear with this. Like this axis is a bit confusing, but it's the minority carrier distribution. They are plotting NP in this side, PN in this side. Okay, just that.
Yeah.
Larger diffusion length. Actually, the values are not given, but I'm just giving the question. You can just looking at the graph, you can tell. Okay, so the xn xp values, this np at minus xp, npn at xn, these values are not given. This how the exponential decay is happening, those values are also not given. But the question is, just by looking at the graph, which region exhibits a larger diffusion length of minority carriers. Option A is P region. So what is the answer? Again, how you look at the graph, that can be different, but just by looking at the graph I can see that this diffusion length, because this is the x-axis, this n side diffusion length is higher if I consider till say this point and say this point. Okay, so just by looking at the graph, it is the n region where the diffusion length is more. Okay, that means our LP is higher than LN. The values are not given, so I'm just looking at the graph and saying this. You can clearly see this XP and XN, that XN is greater, but This is not very clear, but if you look at the graph carefully, you will be able to see. Next is a numerical question. So if the depletion region width of PN junction increases from 150 to 300 nanometer due to an increase in reverse bias voltage, by what factor the junction capacitance changes? We know that with more reverse bias voltage, the depletion width increases, and when the depletion width changes, the depletion capacitance or the junction capacitance changes. So remember this junction capacitance and the depletion capacitance, so they are both the two names. So what is the factor by which junction capacitance changes? So that is the question. Okay, two. Actually, yeah, I mean, you are doing it correctly, but your process is like opposite. Okay, so we know that depletion capacitance or junction capacitance is epsilon silicon by W depletion. Okay, see, this is a bit confusing. These two options are given. That's why you have to be careful. So C1 is our epsilon silicon by 150 nanometer, right? And C2 is our 300 nanometer. When we say that how much it changed, we do with respect to the initial value. So this will be our C2 by C1. Okay. We always take the difference with respect to the initial one. That's why these options are confusing, and both the options are given. This is 150, so this is 0.5. Okay. So the answer is B, 0.5. I think you did the opposite. Yeah, so this is the answer. So you can also calculate by how much the reverse bias voltage is changing. If you remember how reverse bias voltage, how it depends on the depletion capacitance, inversely proportional to square root of VBI minus VA or VR. So the built-in potential of an abrupt PN junction is 0.75. So VBI is 0.75. If its junction capacitance has reverse bias of 1.25 volt is 5 picofarad, what is the junction capacitance for reverse bias 7.25 volt? Okay. The options are given. You can try the calculation. We know that junction capacitance or depletion capacitance is proportional to 1 by square root of VBI plus VR, right? This was the equation minus VBA because our VR is negative already, so this is VBI plus VVR. So we'll use this equation, we use this relation. So our second junction capacitance by first junction capacitance will be square root VBI plus VR1 by VPI plus VR2. So this ratio is 0.75 plus 1.25. So what will be this value? You also have to do the calculation. 0.75 plus this is 0.5. And first junction capacitance is 5 picofarad. So our second junction capacitance is into 5. I need the calculator for this. Is the answer D, right? We can do one or two more questions. So ND equal to NA equal to 10 to the power 16, that is given. Ni is given as 1.5 into 10 to the power 10. dt is given 25. What is the unit of diffusion coefficient? Centimeter square per second. dn is given as 10 centimeter square per second. Tau p equal to tau n, these are minority carrier lifetime, as 5 into 10 to the power minus 7 second. And epsilon r we know for silicon it is 11.7, 11.9. Okay, this is 11.7. So determine the ideal reverse saturation current density. So this is the question. We have to determine Js, reverse saturation current density. So let's solve this. We know that Js is Q, like outside dn ni square ln by na. So this is the electron current component plus dp ni square by lp into nd, right? So dn and dp is given, ni is given, nand is given, ln and lp we have to calculate. So ln, how we calculate it? dn by tau n, this will be what is dn? 10 into 5 into 10 to the power minus 7. So write it in centimeter. Everything is given in centimeter. So this will be, I have already calculated it earlier. So 36 into 10 to the power minus 3 centimeter. Please check the calculation again. And LP will be dp into tau p, that is 35, no 25, okay, into 5 into 10 to the power minus 7. This is 3.535 10 to the power minus 3 centimeter. So Q is 1.6 into 10 to the power minus 19. Dn is 10. Ni square 2.25 into 10 to the power 20. 2.236 into 10 to the power minus 3 into 10 to the power 16. Plus 25 into 2.25 into 10 to the power 20. So this value, please do the calculation by yourself also, check whether I am correct or not. This will be approximately 4.15 into 10 to the power minus 11, and what is the unit? That will be ampere per centimeter square. Okay, this is current density, not current. Okay, I hope this calculation is correct. Please do check once. Okay, this is a theoretical question we have already discussed. So the question is, what is the main difference between Jenner and avalanche breakdown in in terms of carrier generation. Zener involves tunneling. This is the correct answer, right? And avalanche involved impact ionization. Okay, this is the correct answer, option B, but I'm writing all the options. I mean, it depends on like at what voltage it happens, and depends on the type of the material also, whether Jenner will happen first or avalanche will happen first. Okay, because you remember the tunneling, for that the band gap or the barrier should be small, right? That is what we learned in quantum mechanics. If there is a small barrier, the probability that electron will pass is higher. If the barrier height is say very high, then the probability of finding the electron outside the barrier will be like almost negligible. Okay, so the tunneling will depend on that material aspect, and then avalanche, it depends on the electric field. Okay, so whether what phenomena will occur first, that depends on the material as well. That's right. Low voltage. This impact ionization, this is known as the avalanche multiplication, because each time one electron hits, creates an electron and hole pair. That electron and hole pair can create now like 4, because it will like there are 2 electrons now. Okay, so this is known as the this is like a multiplication. It's known as that. We have 5 more minutes. I want to give like one small question. Okay. increases linearly with increase in the forward bias voltage. I'm not writing everything. Okay. So, what is the correct answer? What do you think? See, this you can see. Okay. See, we are considering. Actually, the correct answer is B. I'm telling you how. The question is on forward bias voltage. What I mentioned earlier, that you can do the calculations like how the depletion capacitance, what is the value, what is the diffusion capacitance value, all these things. So in forward bias, our diffusion capacitance is significant. We consider diffusion capacitance. How exactly? Let me tell you. Can do this further also. Okay. So this excess carriers actually changes with the forward bias voltage, right? Change in carrier with respect to bias. So that is the definition of this capacitance, right? C equal to dq by dV. So in forward bias, we actually change this minority carrier concentration. Of course, this depletion width also changes, but that is not significant. That is significant in reverse bias case, because in that case, the depletion width changes significantly. So in case of forward bias, this injected minority carrier changes. So this carrier changes due to the applied forward bias. So this capacitance is known as the diffusion capacitance. Okay. And so we know that our diffusion capacitance is dominant in forward bias. That will change with respect to the change in forward bias. And how it will change? See how the charge dq changes with respect to dv exponentially, right? Where we are changing this va with some factor. If we change it linearly, we increase, we actually get an exponential increase of the injected carriers, exponential increase of the charge. Okay, so diffusion capacitance changes exponentially with respect to the applied bias voltage. Okay, so the correct answer is this one. With voltage, that is forward bias voltage, carriers changes exponentially okay. These are injected carriers, and therefore C diffusion increases exponentially with increasing VA, that is the forward bias voltage. Okay. I hope this is clear. Okay, so we are almost time. If you have any quick question, then you can ask. Otherwise, I will stop the session here. Okay, you are welcome. So if there is no question, then thank you. Let's meet in the next week, next Tuesday from 6 to 8. Okay? Thank you for attending the session. I hope this was useful.